Hi, welcome to Practical Principles of High-Speed Design. On today's class 2, we'll discuss on crosstalk, why crosstalk occurs, how to address the crosstalk issues, and how do you mitigate crosstalks. So we'll start with our first slide. Introduction. So today we'll give an introduction on crosstalk. So crosstalk is one of the families of signal integrity. It's an SI problem, and the crosstalk occurs basically when there is a mutual interference of any two parallel traces routed nearby, and that mutual influence is called crosstalk. Crosstalk can be like a two magnetic fields that interacts, which causes a cross coupling of energy between signals, which is known as crosstalk. And it's a form of EMI or noise coupling, and it can be a radiated electric and it can be magnetic fields. So influence of two parallel traces is the main cause of crosstalk, and with these parallel traces, one would be aggressor, another would be a victim. So two energy coupling types are caused by these crosstalks. One is mutual inductance, that is caused from the magnetic field, and second is on the mutual capacitance, which is from the electric fields. Here is on coupling. So coupling can be of coupling is an undesired one, and its undesired coupling is also known as crosstalk. Coupling are of two types. One is capacitive coupling and inductive coupling. Parasitic couplings can occur anywhere along the line, which is also referred as near end crosstalk, which is NEXT, and far end crosstalk, FEXT. As in the diagram you can see, the current is flowing on a wire conducting current, and there is an adjacent wire, and there is an electromagnetic flux lines which is causing here. Mutual capacitance, which is also called as capacitive crosstalks. The coupling of two electric fields when a current is injected in the coil line proportional to the rate of change of the voltage in the driver. This mutual capacitance also causes positive waves near both ends of the transmission line. So whenever there are two circuits, that is, there is a mutual capacitance. So a voltage is in one circuit will create electric. So mutual capacitance couplings between two circuits simply a parasitic capacitor connected from circuit A to circuit B. So by this, the mutual capacitance C between two conductors is defined as the amount of charges that can be stored on each plane Q per unit of voltage difference between the planes V. So where we derive Q is equal to CV. Capacitive crosstalks will continue. So when you have a mutual capacitance, that is proportionality factor by which a current is induced in a circuit in response to a voltage change in another circuit. So meaning if you see the diagram or presented here, the mutual capacitance, which is called as Cm, is injects a current, induced current Lm into a circuit B proportional to the rate of change of voltage in circuit A, whereby the induced currents in a circuit can be given in the equation as below, like mutual inductance is equal to capacitance, mutual capacitance dV by dt. Mutual capacitance coupling. So a noise capacitively coupled into the victim net will travel in both the directions. The near end would be towards the aggressor driver, also known as backward crosstalk or NEXT, which is near end crosstalk. The far end is away from the aggressor driver, also known as forward crosstalk or FEXT. Near end and far end capacitance crosstalks are always at the same polarity. So near end pulse arrives in successions like wide pulse, etc. Far end pulse arrive at the same time, but like with longer amplitude and smaller width. As I was saying in the diagram, with circuit A to circuit B with near end and far end, with the driving signals, you can see the mutual capacitance that is formed. Mutual inductance, which is also known as inductive crosstalk, a magnetic field that would cause induced current from the driven wire to appear on the quiet wire. So this mutual inductance causes positive waves to appear near the transmitter end of the quiet line, which is near end inductance, and negative waves at the receiver end of the transmission line, which is far end crosstalk. So mutual inductance is present wherever there are two loops of currents. These current loop produce magnetic fields which interact with one another proportional to the rate of change of the current within the loop. So that is called mutual inductance or inductive crosstalk. Mutual inductance, which is proportionality factor by which a voltage is induced in the circuit in response to the current change in the another circuit. Like as you see in the diagram, a mutual inductance Lm injects a noise voltage V into circuit B proportional to the rate of change of current in circuit A. Thereby the induced voltage in a circuit can be given in the equation as below, like V is equal to Lm mutual inductance di by dt. Mutual inductance coupling. Noise inductively coupled in the victim net will travel in both directions, that is near end and far end. Near end crosstalks and far end crosstalk have opposite polarities, and near end pulses arrive in succession like wide pulses. Far end pulses arrive at the same time with larger amplitude and smaller width. As you can see in the diagram, there is a near end and far end with a driving signal where you can see a mutual inductance is formed. Microstrip crosstalk. Crosstalk can occur when a signal jumps from one trace to another. It's a phenomena that is unintentional and often which is unwanted. So microstrip roads can see decrease in mutual capacitance depends on how much dielectric material is above the trace. Microstrip routes will see no increase in mutual inductance, and the result is always an increase in far end crosstalk. You can see the diagram where you have a height of a PCB stack up and with the two traces running with a spacing S. And on the right hand side you see the layer stack up details, how it is framed on a microstrip and to other strip lines with stack up editor in from Expedition tool from Metro Graphics. Crosstalk reflections. If the injected noise hits an unterminated load, it will reflect. So with any transmission line, a lack of terminations at the receivers produces reflections, and which would double the voltage of any incident spray. So basically it should be any lack on termination of the receiver would produce the reflections, and the reflected crosstalks can be double than the initial crosstalk with an unterminated load. So a terminator on the victim net at the near end can stop the crosstalk from reflecting to the far end, and a terminator on the aggressor net at the load can stop the signal from reflecting, causing more crosstalks. So basically when you have near end and far end the drivers receiver, and you can see both mutual capacitance and mutual inductance when you drive the signals, and this is how the crosstalk reflections will occur if it is not properly load is not unterminated, if you have an unterminated load. Crosstalk mitigations, like if you use strip line so that no foreign crosstalks will occur, and any loosely coupled allows to reduce dielectric height and less fringe fields. So microstrip should be very short. So if you need microstrip traces, then use a large separations. Use a formula like spacing is greater than 3W, and reduce the coupled length as much as possible. So those are the points to take up on crosstalk mitigations. And techniques of reducing crosstalks. So as a PCB design techniques, if we adhere to some PCB designs rules that can significantly reduce crosstalk in microstrip or any strip line layout. So we will go through the points, like one, like widening the spacing between signal lines as much as routing restrictions allows. So you widen the space between the signals, so that would reduce the crosstalks. And secondly, like design the transmission line so that the conductor is as close to the ground plane as possible. So this couples the transmission line tightly to the ground plane and helps couple it from adjacent signals. So you should have a close ground plane as near as possible. And third is like you use a differential routing techniques wherever possible, especially for any critical signals. And fourth is like route signals on different layers, like orthogonal routing to each other if there is a significant coupling. So that's why XY or orthogonal coupling, you follow that. And fifth is like minimize the parallel run lengths between the signals. So try to minimize it, and route with short parallel sections if you cannot avoid it, and minimize along long coupled sections between the nets. So these are some of the techniques for reducing the crosstalks. Near end crosstalks. So this will occur when you have an aggressor and victim, with transmitter and receiver, with driver and receiving end on aggressor and victim side, and it will all form of coupled lines. This will occur, but it also depends upon the mutual capacitance and inductance. So on the right side we can see the ICX probe of a near end crosstalk, how it looks, how the near end crosstalk would form here. And second is on far end crosstalk. So aggressor and victim with transmission receivers, with driver and receiver, as you see how it flows. And this only in homogeneous couple lines, like example like microstrips. And also depends upon the difference in velocity between even and odd propagation modes. And towards the right you can see the ICX probe of far end crosstalk, how it appears. So how do you mitigate crosstalk? Mitigating crosstalks, like if you sting the aggressor, separating groups of nets, meaning separating groups of nets according to their signal amplitudes. Like say suppose you have larger voltage affecting to a smaller voltage, then you can separate those groups of nets. Second, on reducing the coupling, like if you can provide a solid reference plane or adjacent reference plane below or above the signal trace, that would help to control the crosstalk between it confines rate and recurrence. Third is by keeping the loop area small. So trace which is adjacent to one power or ground plane and then jumps through a wire to run to other adjacent to a different power or ground plane. Guideline is to place a bypass capacitor nearby to help retaining any signal current follow along. And fourth is like reduce the number of aggressors. So this, if you have an FPGA a kind of design, then it can be accommodated in some systems by skewing the clock used on various banks of logic, such that the aggressor changes state at slightly different times. And you try to reduce the number of simultaneous switching signals with data coding. So with this, few of the guidelines, we can try to mitigate the crosstalk. Ground traces. A ground trace is nothing but it's a grounded trace that is placed on the both sides of a noise sensitive traces. In the past, guard traces were used on all the crosstalk sensitivity signals. But the results reinforced the practice that fewer crosstalk problems occurred in the test. But guard traces put a heavy burden on the routing of the board because of the spacing. Guard traces, the great results from the guard traces are mostly attributed to the increase in trace separations and not the guard trace itself. This is only true if there is an adjacent plane. Yes, that is true. Since if you can increase the trace space as much as possible, that means basically you can mitigate the crosstalk issues. And with the digital circuits, if you allow enough room for the guard traces, then crosstalk protections has been achieved. So exception is like guard traces are still sometimes necessary with analog circuits that have higher noise sensitivity. So how crosstalk influence on trace impedance? So can crosstalk lower the impedance on a victim net? Yes. And why? Because crosstalk injects current into a victim net, which is Z equal to V by I. So parallelism also reduces impedance by adding parasitic capacitance. And when a victim's trace impedance is only evaluated, the victim is switching, and it's not always. Therefore, crosstalk will occur any other time. It really has no effect on impedance. Signal sensitivity to crosstalks. So one of the benefits of synchronized design is that all the data lines are evaluated only on clock edges, and so are common immune to crosstalks. They are immune to crosstalk because of the clock edges, and they are synchronized. And because of flip-flops also, because clock to Q delay that we consider. When a large bus toggles, the crosstalk generated will be after the rising edge of the clock. So a synchronized design acts like a noise filter to a crosstalk. Signal sensitivity to crosstalk, or like if you have a bus keepers, can be very sensitive to crosstalk. A bus keeper is a very weak driver that sustains the level on the line when all other drivers try states, eliminates the need for any pull-up resistor. But bus keepers allow stronger signals to toggle the bus when then they will sustain that new level. So crosstalk can flip the state of a bus keeper. So connector basically can cause a large crosstalks because they have no reference plane. So like microstrip type configuration, so far-end crosstalks can be significant, and aggressors surroundings on the victim can cause an additive effect. Like suppose if you have a faster edges on the signals, make the length of connector relatively long. So freak scale is example like a local bus switches to 3.3 volt which in 25 picosecond, and this full edge can transition in about 0.75 inches. In synchronized designs, only the clocks and asynchronous signals are potential victims, as we know that. Sensitivity signals like naming like asynchronous sets and resets, latches, memory strobes, all clocks, mixed voltage designs on CMOS and LVDS or any emitter coupled logic ECLs are all like sensitive signals. Low voltage analog sections inside a digital board can be extremely sensitive to crosstalk. So by doing crosstalk analysis simulations and establishing your PCB design guidelines, remember you should have a complete list of crosstalk sensitivity signals should be established. Like if you see analog, digital part, and a power and a ground plane reference as you have in a board, and you should completely come out with a list of all crosstalk sensitivity signals. Crosstalk Simulators. You have tools like UltraCAD, SciSoft, but as per I observed, the simulators is based on simplified equations and is only an approximations. But in order to get an accurate results in simulation, the simulator must use a field solver. A field solver that basically takes Maxwell's equation and describes the behavior of electronic and magnetic fields and calculates these fields from boundary conditions that are based on your PCB geometrics. Trace, L, inductance and capacitance are derived from the results for transmission line analysis. And for further analysis, you can use interconnectics or hyperlinks tools. Crosstalk budget. How much crosstalk should you allow? So in a synchronized design says that the crosstalk will always follow the clock edge, which implies that the clock is at a stable high with some noise margin. So noise margins are typically about 15% of signal voltage swing. So let's say 1/3 or 5% is allocated to the crosstalk. So for a 3.3 volt signal, the maximum allowable crosstalk is around 160 millivolt. Approach like use ICX or hyperlinks for crosstalk analysis. So for that, you establish the critical nets and noise budgets and perform what-if simulations to establish trace separations rules. Analyze route to make sure crosstalk levels weren't exceed. When routing resources allow it, critical nets are routed on dedicated layers. So critical net always have an adjacent reference planes. And final crosstalk analysis to be done after the board is completely rotated. So we never know because an autorotator what it can do. And a split plane approach is used to isolate different circuit types like analog, ECL, etc. Bypass capacitors use like 0.1 microfarad and 0.15 microfarad are scattered on the board to minimize loop areas. So they will equalize the power and ground planes. Similarly, planes are wired together to minimize the loop areas. So we will summarize the crosstalks now. Crosstalk summary. So as you see in the diagram, like when traces are close together, a change in current flow in one trace will cause current to flow in an adjacent trace. So basically, in aggressor traces induce currents in adjacent victim traces. So any change in current flow only occur during the aggressor rising and falling edge. Crosstalk summary. Crosstalk is caused by mutual inductance and mutual capacitance between two lines. Adjacent reference planes help to significantly reduce crosstalk. The amplitude is directly related to the proximity of the two lines. Absolute crosstalk amplitude is proportional to slew rate dV by dt or di by dt, but not just the rise time Tr itself. A package and connector crosstalk may be a concern, possibly no adjacent reference plane on that. So you can reduce crosstalk by reducing the trace impedance. To reduce impedance, you either brought the traces closer to the reference plane, which is good, or you increase the trace with less mutual inductance directly related to the inductance of the trace. So crosstalk would cause switching noises to appear on the victim traces that would otherwise be quiet. And you can see in the diagram like how the crosstalk induced noises with victim and aggressors. On PCBs with adjacent ground planes, reverse crosstalk is a major problem. So reverse crosstalk can reach a maximum very quickly depending on the edge rate. An edge rate of suppose a 1 nanosecond with propagation delay time of 1 nanosecond per 6 inch, which can be a maximum distance of 3 inches. So terminations only stop crosstalk from reflecting and getting worse. It does not stop the initial crosstalk by itself. With digital noise margin and adjacent planes, guard traces aren't necessary if you still allow for the increased trace separation had you actually put the guard traces in. So we only look at like one aggressor, one victim scenarios in this case. But totally, the crosstalk is the sum of a crosstalk from each of the several nearby aggressor, and there is a summing effect on that. So you can see the picture like crosstalk is induced by the return current path, source and sink with ground plane, where you have reference of VCC and ground. References you can refer with on more details on signal integrity, like from Eric Bogettin, signal integrity simplified and high-speed digital signal, high-speed digital design and high-speed digital system design from Martin and Stephen and Garrett and James for your further reference. So thank you for watching this presentation on high-speed signal integrity or high-speed design on Crosstalk. Thank you.